Hello everyone and welcome to the today's recorded session on dynamic programming. This topic of dynamic programming is a very important topic. And why I am saying this to be very important? Because most of the product based companies, be it Google, be it Amazon, or be it any other company that gives you a lot of package, they discusses the questions basis on them. So in their interviews or in their coding rounds as well, most of the questions are in this category only. These questions also test your analytical skills a lot. So it is very much helpful to know about this topic, as this topic gives you a lot of tools, a lot of mechanisms in order to solve a particular kind of problem in a very efficient manner, in order to reduce the time complexity of the program, and also to make some optimization problem very easy to us. So what is dynamic programming? So dynamic programming is a topic that can have different kind of problems. But just remember that what thing you have to find out in a question for being a dynamic programming question. So first of all, we will understand what question that you are going to have, that does that question belongs to a dynamic programming problem or not. Let us first discuss on that. Okay, so let us discuss the problem of solving with dynamic programming on the basis of a very famous problem. I hope that all of you know this problem. This problem is known as the Fibonacci numbers. What are Fibonacci numbers? First, let us take a look at that. The first two Fibonacci numbers are 0 and 1. Okay, these are the first two Fibonacci numbers. Then the continuation is like this. I will just explain you the rule behind it. Let me just first write the first few Fibonacci numbers. Okay, so the rule behind writing these Fibonacci numbers is that the nth Fibonacci number, that is f of n, is equal to the sum of the previous two Fibonacci numbers. That is f of n is equal to f of n minus 1 plus f of n minus 2. You can also take a look at this thing in this way. Just one thing, that the first two Fibonacci numbers, that is the f of 1 is equal to 0, the first Fibonacci number is 0, and the second Fibonacci number is equal to 1. So this is the recursive formula for finding the nth Fibonacci number. Okay, here now you can see over here that this number over here, that is this 2, is the sum of these two numbers, that is 1 plus 1 gives you 2. Similarly, if you consider this 3 over here, this is nothing but just the sum of these two Fibonacci numbers, that is 1 and 2. And accordingly, the other numbers are also computed in this way. Like if you see this 13 over here, this is the sum of 5 plus 8. So this is what Fibonacci number sequence looks like. And this is the recursive formula behind it. We can also code this recursive formula with the help of a coding language. So let me quickly code this up for you all. So the code is really very simple. Let me write the code. Okay, so this is the code for the recursive formula that I just wrote over here. You can clearly see that in this particular case, I have made this recursive function that calculates the nth Fibonacci number. This function takes one argument, that is an integer n, the nth Fibonacci number. This is the base case, that if it is the first Fibonacci number, then you should return 0. If it is the second Fibonacci number, then you should return 1. And the recursive case is that the nth Fibonacci number is equal to the sum of the previous two Fibonacci numbers. And for testing this particular code, I have just printed the value of Fibonacci of 8. That is the value of the 8th Fibonacci number. So as you can over here see that the value is coming out to be 13. And yes, of course, that is the correct answer because the 8th Fibonacci number is 13 only. So this is the brute force approach for this. What is a brute force approach? It's a kind of an approach in which you do a particular problem, you solve a particular problem in the worst possible way, not the most optimized way, in the worst optimized way. So like over here, you can see that what is the complexity for this program. If you will find the complexity of this program, this is approximately equal to big O of 2 to the power n. And this is a very huge time complexity. So if I consider a value of n to be around 10 raised to the power 5. So in this particular case, if I would have this particular complexity, then this would be a very huge time, because 2 raised to power n is an exponential time complexity and it is pretty much huge. Now here our friend dynamic programming comes into the picture. It would help us to reduce this time complexity to a lot. In order to understand what do we mean by this thing, let me open a new whiteboard for you all. Okay, so now let us try to find the fourth Fibonacci number, and let me draw a tree for you guys. So I am going to draw a tree. So I am trying to find the fourth Fibonacci number. So I have made a node with the value 4 written on it. Now according to the recursive function, the fourth Fibonacci number is basically equal to the sum of the third and the second, right? So it is basically nothing. It would call two other nodes. One node would be 3 and the other node would be 2. So basically this Fibonacci number of 4 would be the sum of the Fibonacci number 3 and number 2. In turn, for calculating the 3, I have to also calculate like this, right? I have to calculate the Fibonacci number 1 second and the Fibonacci number 1. And for finding the Fibonacci number 2, I already know that Fibonacci of 2 is equal to 1. So this would result in a value of 1. Similarly, this would result in a value of 0 and this would result in a value of 1, because these are the base cases, right? Now Fibonacci of 3 is what? It is the sum of the two subnodes over here, the two children over here, right? So the sum of this second Fibonacci number and the first Fibonacci number, 1 plus 0. 1 plus 0 is what? It would give you the third Fibonacci as 1. Okay, and Fibonacci of 2, we already know that it is equal to 1. And this 1 and 1 will give you another sum, that is 1 plus 1, that is equal to 2. So in this way, we have got the Fibonacci of 4 as 2. So this is our answer. So this is how a recursive problem works. This is how a recursive function works. And you can also see here that the fourth Fibonacci number we are having is equal to. So we have just shown that how a recursive function works. Okay, now let us take a look at a bigger way, okay, a bigger number. So let us try to find the fifth Fibonacci number and see how the Fibonacci numbers are calculated repeatedly again and again. Now let us try to find the Fibonacci of 5, the fifth Fibonacci number basically. So let me draw a node 5 over here. Now of course, for finding the value of 5, we have to call in the Fibonacci of 4, the Fibonacci number of 3, we have to find their sum, right? And for 4 also, we have to find the Fibonacci number 3 as well as the Fibonacci number 2. And for 3 again, we have to find the Fibonacci number of 2 and the Fibonacci number 1. And for 3, we have to find the Fibonacci number 2 and 1. So of course, these are the base cases. So 2 would return 1, it would return 0 because the first Fibonacci number is 0, the second Fibonacci number is 1. And the sum of them, 1 plus 0, would be the Fibonacci number 3, that is 1. This is also 1. And 1 plus 1 would give you 2, so Fibonacci of 4 is 2. Now we have to go to the right side. The Fibonacci number 2 is 1, the Fibonacci number 1 is 0. Okay, 1 plus 0 would give you 1. So over here 1 would come. And then finally 2 plus 1 would give you 3. So we have got the answer that the fifth Fibonacci number is equal to 3. But now there is a problem over here. You can take a look at the problem that in turn to find the Fibonacci number of 5, I calculated the Fibonacci number 3 two times. Can you see over here? First time I calculated it over here, and the other time I calculated over here. I know that the Fibonacci number of 3 would be 1. So if I have calculated this thing one time, if I have already calculated the Fibonacci number 3 one time, then what is the need to calculate it again? As over here you can see that I am calculating it over here again. So don't you think that it is a repetitive task? It's a repetition of task, and it's kind of a wastage of computation time. So how we can stop this? We can do one thing, that we can make an array kind of a thing. We can make a visited or a dynamic programming array kind of a thing that would store whether I have calculated an nth Fibonacci number before or not. What do I mean by that? Let us take a look at this thing. Okay, so here you can see that I have made a DP array. In the DP array, initially all the values are equal to -1. The DP array is of course the size of our input, the size of what Fibonacci number I have to find. -1 signifies that it hasn't been calculated. -1 means that the ith Fibonacci number is not calculated yet. Okay, so I made my recursive call at 5 over here. Okay, then I made a call for 4, it gone to 3 and 2, then 2 and 1. So when I came to 2 and when I came to 1, I know the Fibonacci number 2 is 1 and Fibonacci number of 1 is 0, right? So this means I have calculated it. So in my DP array, I'm going to remove it. I'm going to change them. The first Fibonacci number would become 0. The second one would become 1. Okay, and they would be returned over here. Okay, it would be returned over here, and I would get the sum of them, 1 plus 0 as equal to 3 as equal to 1. And it means that I have calculated the Fibonacci number 3 also, na? So at this place of -1, I'm going to put 1, the answer for Fibonacci number of 3. Now this thing also I have calculated the Fibonacci number of 2 over here, as this has been already calculated. How I knew that it has been already calculated? Because in the DP of 2 over here, you can clearly see that it is not equal to -1 now. It is something other than -1. It means that it has been already calculated. So over here, I'm going to put 1 over here. I'm going to see what value is and I'm going to return it over here. Okay, now 1 plus 1 would give me 2. Initially, the fourth index of DP array, or the Fibonacci number 4, wasn't calculated, right? Because it was -1. But now I have calculated it and it is equal to 2. So I'm going to store over here 2. As good as that. Okay. Now for 5 also, I'm going to this function call now. But now the magic happens. The dynamic programming magic happens. What's that magic is? That there are two things. Either I should go to the below branch over here for calculating this Fibonacci number, the third Fibonacci number again. But if I take a look at the DP array and at the third index, I see that the DP of 3 is not equal to -1. It is a value that is other than 1, other than -1. And the value is equal to 1. It means that I have already calculated that what is the value of the third Fibonacci number. And as I have already calculated it, so there is no need to go below in this graph, further depth in this graph, in this particular tree. So I will just find that what is the value at DP and 3. I will just not execute this I will just don't go further inside this particular tree and just return the value, whatever is written in the DP array of this thing. And here you can see the value is 1. So 1 is returned over here and 2 plus 1 would give you 3. So over here it would become 3. In this way, in a mere O of n algorithm, I have finally calculated the DP of 5, or the fifth Fibonacci number. Isn't it a great way that if I have calculated the third Fibonacci number, I am not going to calculate it again, as I'm storing my results in some DP array, in some pre-computed array. So that's why this DP array is very, very important, because it helps us in finding that whether you have calculated a particular ith value before or not. So that's why this DP array is very, very helpful to us in order to avoid repetition of calculation. There is a very famous quote that if you have done a task before, then why you need to repeat it again? Just use your memory and find that if you have already done that task, then what was your answer. Just use that answer and proceed further. Don't go deep inside for calculating that answer again and again. So that's the major thought, that's the major philosophy behind dynamic programming. So let us just quickly write the program for this particular case. Alright, so over here I'm going to make a DP array. Now let us make a DP array of size 1000. I'm assuming that the maximum input I'm going to get is of 1000 only. And like I told you that initially all the values in the DP array would be equal to -1. And what -1 signifies? -1 signifies that I haven't calculated the ith Fibonacci number before. Okay. Now over here I'm going to check. If dp of n is not equal to -1, then I'm going to return dp of n. What this statement means? It means that if I have already calculated the nth Fibonacci number, then its answer would be stored in the nth index of the DP array. So I will just return it. There wouldn't be any need for calling this particular recursive call again. So that's why I have basically reduced my task, reduced the repetition of task. So already know the answer, right? Answer for n, just return it. Okay, and if it was not equal to -1, it means that I have to basically find that particular answer by calling the recursive calls. So I will just make the recursive calls, and this answer I would store in dp of n, because it would be some number other than -1, and whatever that number is, if this n function call comes again, then the answer would be stored in dp of n. It won't be -1 then, and it would just simply return, so that I don't need to calculate the nth Fibonacci number again and again. In this way, the complexity has become O of n. And this is a very, very, very important topic and a very important way to optimize your problems. So I can very easily calculate the, let's say, Fibonacci number of 10 over here. Let me calculate it. So you can see that the Fibonacci number 10 is coming correctly. So that's how this particular code would work. So we have seen that what dynamic programming is, what's the need of dynamic programming, and why and how it can reduce your complexity very, very greatly. So if you have got a recursive problem, and in that recursive problems, you are finding repetitive task, and that is having an optimal substructure, then you may get an idea that okay, you can use a dynamic programming approach. And also this dynamic programming approach over here is known as memoization. Just remember, this approach is known as memoization. So once you practice more and more problems based on dynamic programming, you will get handy of tasks about when to find and how to find whether a particular problem belongs to dynamic programming or not. So this is a very important topic for product-based companies, and I hope that you would crack these problems and practice more and more. So thank you for watching this recorded session, and have a great journey ahead.